In this video, we're going to develop two special limits. And we're going to use the squeeze theorem, also known as the sandwich theorem, to help us develop the first one. And then we'll use the first one to help us do the second one. And so these are two limits. I mean, this isn't something we do often, but we do have to understand where these limits come from, and then this is a limit that we're going to use later on in our development of calculus. But we're going to go ahead and get these limits out of the way in this section. Now the first limit is this. What is the limit as x approaches 0 of the sine of x all over x? Now the first thing we would want to do, of course, is substitute in 0 for x, and then when we substitute in 0 for x, we get 0 over 0, which is indeterminate. Now, if we were to do a quick sketch of this, I'm not going to make this super accurate. What happens is there's a little hole there, and then this thing kind of goes like this and dies off. So this is our key point. What is this value right here? And we can numerically do this, but you know, in calculus and in math classes, beyond calculus, we do have to get used to the idea that we have to prove things are true. We just can't sit there and say, oh, well, the professor or teacher told me this, therefore I'm going to believe it's true. You have to start getting used to the idea that you have to be shown by the teacher or the professor that it's true and that it's been proven and why it does work. And so that's what this is all about. I mean, yes, we could probably, with our nice calculators today, quickly figure out what this value is numerically, but we want a better proof of that. All right, so to prove this, let's look at a really, let's see, we first need a diagram. It's actually kind of a neat little proof. So we're going to take a quarter of a unit circle. So we'll take the first quadrant of a unit circle. This is a unit circle. Let's see if we can do this well. That's not too bad. All right, so if this is the unit circle, this is our origin, O, which has to have the point 0, 0. And this is our, I'll just call this point A. Now, that's 1 unit, so it's got to be the point 1, 0. Easy enough. And then what we're going to do is up here, I'm going to create a right triangle. Right triangles are always handy. And create a triangle that goes from this point A up, and then from the origin up here, and we'll call this point T. Now we're not going to put a number on that point T because, well, it's going to be based on this angle theta. So as we move theta, you know, up and down, change its angles from, say, 0 up to, 90, well, can't go to 90, but 89.99, how long t is it changes. So let's first go ahead and figure out what is the area of this triangle. So what is area of triangle OAT? OAT. Alright, well, we know that triangle is 1/2 the base times the height. Well, the base of this is, well, 1, so that's easy enough. 1/2 times 1. Now we need the height of this. Alright, well, this gets a little tricky, but we're actually going to go ahead and I'll do a little side work over here. Well, this is a right triangle, so let's go ahead and use right triangle trigonometry. So if this is our angle theta, and we have this side and we need the opposite, well, that's the tangent. So we know the tangent of theta is the opposite h over the adjacent 1. So that means our height is just the tangent of theta. Easy enough. So put that up here. So So the area of triangle OAT is the tangent of theta over 2. That's kind of neat. Okay, now we're going to build another little triangle, and this one here, we're going to go from where this side intersects the that point right there. We'll call that point P. And so now I'm going to connect these two. And so we have this little triangle OAP right here. So let's find the area of triangle OAP. OAP. Now we need the area is going to equal 1/2 the base times the height. Now the base hasn't changed, that's still 1. So 1/2 times 1. But our height is no longer this one here. You see, this was the tangent of theta. But now here's our new height. And so we got to figure out what that one is. Well, we're going to kind of change this around. Instead of thinking of our right triangle right here, we now have a little right angle here. And so we have this little right triangle. And the reason we're going to use this little right triangle is because we know that the distance from here, from O to P, is also 1. So let's look at a little side work here. So if this is also 1, then we have theta. We want this side H, and we want this side over here, which is 1. So that's opposite over adjacent, which is the sine. So the sine of theta is, I'll call this H2 over 1. So that means H2 is the sine of theta. So this is the sine of theta. So that means the area of triangle OAP equals the sine of theta over 2. Alright, now the last thing we need is we have a sector. So if you remember from trigonometry or your study of geometry, a sector is basically a portion of a circle. It's kind of a piece of the pie. What is the area of that? So let's go ahead and look at area of sector OAP. So the sector would be from O to A along the curve of the circle to P and then back down. It's a little bit bigger than the triangle OAP, which is going to be important here pretty soon. Well, most of you probably don't quite remember what the area of a sector is, which is fine. Let's see here. Area of a sector is 1/2 r squared theta. Now, if you kind of want to think about the logic behind that, and here I'll come down here. If the area of a circle, this is how I used to teach it back in trigonometry and geometry. The area of a circle in general is pi r squared, right? Now we don't have a full circle here, we only have a portion of a circle. So what we wanted was, we got to multiply this pi r squared by some fraction. And the fraction we used was, well, we have this angle theta, that's in radians, and we know that there's 2 pi radians in a full circle. So our fraction was theta over 2 pi. So if I take theta over 2 pi and I multiply that by pi r squared, the pi's cancel out, and then we basically get theta over 2 r squared. And if you rewrite it, it just becomes 1/2 r squared theta. So that's kind of the general logic of where does the area of a sector come from. Sometimes that's a hard one to remember, so if it ever comes up, it's a good way to think of it. You have the area of a circle and you need a fraction of that, so you multiply by theta over 2 pi. That's how we also developed the one for the arc length. It was kind of the same logic. Anyways, so here is our area of a sector. And, well, in this case we have theta. The radius is just 1, so this is going to be 1/2 times 1 squared theta. So area of sector OAP is just theta over 2.